crying's not gonna get you anywhere.
I'll stop.
Why?
Last night in that restaurant, I kept trying to tell
Come
you.
on, get down to it.
Before they let me out, they took me to the DA's office.
O'Neill? His name's Walter O'Neill.
Yeah, that's right, that's his name.
All right, they took you to his office.
He asked me a lot of questions, mostly about you.
Not me.
About you and me.
Huh?
He kept asking me if I knew why you came here. He asked me that a couple of times.
What else?
Oh, a lot of questions I forget.
Remember.
My head's mixed up.
Well, the goons, the ones who worked me over.
They just wanted to scare you. O'Neill doesn't want you in town. They said if I didn't play with them, I'd go back to jail.
Who said that, O'Neill?
No, the other man, Mr. O'Neill, wasn't there by then.
Cute kid.
They said they wouldn't hurt you.
Much.
No more parole, they said, if I went for it. I'd do the whole 5, they said, if I didn't. I went for it.
If you love listening to this show, please consider giving a rating and a review on Amazon Alexa or wherever you listen. We want to continue bringing you this amazing content, and part of our ability to do that means that we need a big audience. Now, it may not seem like much, but rating and reviewing the show will help more people find us, just like how you found this show. Simply on any podcast platform, search for a show, scroll down to the bottom, and push 5 stars. It's that easy. Thanks for supporting the show. Today, I'm joined by Dr. Luuk van Dijk, CEO and founder of Daedalean, a startup developing flight control software for autonomous flight. Welcome to the show today.
Thank you very much for having me.
All right, so Luuk, you've held software engineering positions at Google and SpaceX. Right. And I wonder, when you think about your experience there, as well as your other kind of collective career experience, how did that prepare you for the role that you're currently in and the focus of your current startup?
That's a very good question. So when I joined Google in about 2005 in Zurich, and for various reasons, I had an opportunity to move to Los Angeles to join SpaceX. And a couple of experiences there shaped me for preparing what I do today. I think one of the first ones is that I was forced to retake my driver's license in California at the DMV. And a grumpy guy jumped in the car, drove me around the block, and I realized with the state I knew the Google car project to be at that time, which is early 2013, I thought if somebody adds voice interaction, the Google car can pass the California DMV test today. So the idea that you can have the computer not pass the Turing test, but pass the driver's license test, that was sort of lodged in the back of my mind. And then when I joined SpaceX, I learned the corporate legends and the sort of the collective knowledge there, and there was one that stood out that always stuck with me, which that apparently way before my time the SpaceX engineers had this attitude of step aside, you previous generation, let the internet cowboys take us to Mars, and then NASA came in and said, if you don't develop software according to our standards, you're not going to come within 30 kilometers of the International Space Station because that thing is expensive and, it's not like we don't know what we're doing. So then, this is all before my time and, I'm sure some of this is formed by legend, but then new management came in and thought, okay, if you have to follow these regulations, you should not see them as paper hurdles that you have to jump. You might as well embrace them and make them work for you. So at SpaceX, there was this process around design assurance for software development that actually ended up making everybody sleep a lot better because these rockets are dangerous things, and if they blow up on the pad or on landing, which was new at the time, then you want to be sure that you did absolutely everything right to make sure that didn't happen. And so these two things sort of came together in 2016 when I saw a number of eVTOL projects coming up. So the so-called flying cars, electrical vertical takeoff and landing aircraft. All of a sudden, they were popping up in the news. At the same time, people were working on the self-driving industry was sort of booming. There's like 40 startups in the second half of 2015 in this space, and I thought self-flying cars, that would be actually a notch more interesting And then what you would want is you want an autopilot that can pass the exam for human pilots on the one hand. So that was the one idea that was launched. And the other thing I realized is for this, you need these modern robotics and computer vision and machine learning techniques, this AI field, which at the time, the firm belief of everyone involved was you cannot get this certified. And I thought, okay, there's an opportunity here if we can get the regulators, the FAA, and in Europe, the EASA, to see and argue and and reason to them that you've built a safe system building these modern techniques. You've actually drawn the state of aircraft control, avionics, 30 years into the future. Because you may have you mentioned earlier that aircrafts, allegedly they're on autopilot and they fly themselves already. But if you look at the cockpit of a 737 or even a simpler airplane, there's a lot of buttons there, right? So these buttons are there for humans to press. So, and if you analyze it, then a human with almost no instruments can, look out the window, his or her hand on the stick, navigate legally and safely an airplane from start to landing. There are currently no instruments that have anywhere that capability. But a lot of the cruise is automated, sure, and and the instrument landing system is a pilot overviewing it, but it's all not integrated. So I figured maybe I'm getting ahead of myself here. If I bridge that gap of machine learning and the regulator, that would be a massive business opportunity. So that was basically the roadmap we set out on.
Fascinating. And actually, that really dovetails into a lot of the questions I'll be asking. But let's first focus in terms of what are kind of the near-term objectives for your startup?
The near-term what?
Objectives for your startup.
So the absolutely highest thing to de-risk is that you can certify a machine-learned component in an avionics system. So we have projects going on with both regulators to work through that. Already last year, we published the results of a first project we did together with the EASA, the European Aerospace Safety Agency, on concepts of design assurance for neural networks. And we're currently working through a follow-up with them on that project. We have a similar project that I can't say too much going on the other side of the ocean. And the first results will be that we show that the method we developed for proving that neural network is this safe and this number actually holds when you go and fly in the wild, that method works, which will modestly speaking will put the whole industry at a new level. So that's our top priority. Then we have with partner Evidine, which is an established avionics maker, we have a product roadmap coming up, which we will roll out to bring this functionality as advanced pilot assistance to existing aircraft that already fly today. So as a startup, your investors ask, so what's your path to revenue? And then we were lucky to find out that there's already a lot of opportunity in aircraft that fly today. So anything smaller than a large airliner is not as safe as a large airliner. So a large airliner is very safe. Anything that's smaller, there's a lot of headroom in the safety. So we figure that there's some early products we can launch there around detect and avoid and landing guidance. So imagine that your business jet, when you leave your hands off the stick, it will land itself. You say, can it already do that? It can already do that if it's an expensive business jet that has very expensive equipment on board, and it lands in 1 in 60 airfields in the world that has instrument landing infrastructure. But pilots land regularly on 50,000 airfields in the US without this guidance. So these are some of the earlier functions we're bringing to market.
Yeah, I think you bring up some really interesting points, which is that there's just a lot of sophistication when it comes to the larger commercial planes that most of us take for granted. Right. And those do have a lot of advanced capabilities. Yes. And certainly to some extent some of the business class as well, private jets as well. But once you go below those class, and it's a pretty big kind of gap once you go below, is I think everything from maintenance to the equipment to the software. I mean, it can be very lacking in some cases. You may also like our quarterly Astor Perkins event that brings some of the most notable experts and category leading startups in their area of sustainability and human survival on Earth and in space. To register, visit astorperkins.com/events.
If you've been flying in a smaller aircraft with friends, you will have noticed that it's a very manual affair with, levers that you have to pull and, windows you have to look out at, and you have to talk over a microphone to someone on the ground who will tell you where to fly. So the big airliners, on the one hand, they are a testimony to the success of the regulator to make an inherently dangerous activity, flying at 10 kilometers altitude near the speed of sound in a metal tube filled with fuel, inherently dangerous. That the accident rate is as low as it is a major victory for the FAA and regulatory agencies. If you go to smaller aircraft, anything with 19 seats or below, actually the probability of a fatal accident is roughly the same per hour as riding a motorcycle. You have people who don't want their spouse to ride a motorcycle because it's too dangerous. So that's exactly where we see a lot of headroom and a lot of economic advantage of making it safer by helping the pilots to the point where it's better if he or she doesn't touch anything.
Now, there is, of course, a lot of economics that goes into it because in the case of more like a hobby pilot that flies on the weekend occasionally, the kind of capital investment that he's made into that plane, whether it's actually outright owned or leased or some fashion, it's going to be difficult for some of them to make that kind of investment into upgrades.
That's
and
clear.
the other piece of it is it's not just the software, right? Because even if they utilize, let's say, your certified AI-ready, fully autonomous suite at some point, aren't there some additional kind of hardwares and sensors and things that have to be in place to support the software as well?
Yes, and you are right that is actually a barrier for us to go to market. So we were pretty happy to find Avidyne ready. On the other hand, the sensors we use are more or less off-the-shelf electro-optical cameras, so they're high-definition cameras, and they need to feed to a computer that's powerful as my laptop. But both of these are not available currently to aerospace standards. But it's a pretty straight path to get there. So we know what to do. So that's not to de-risk that. It means just to execute the building plan and to get that out there. And it won't have to be aerospace. In aerospace, you pay a premium for the certification anyway, but the cost of goods doesn't need to be prohibitive. But then the flip side is that the market for the small pilots is also limited. So your average private pilot owner does not want to spend $90,000 on a piece of equipment. Especially many of these people fly this thing for fun, right? So if you ride a horse, you're not going to be helped with an autonomous horse rider robot because where's the fun in that? But for the more commercial use, you can think of going to simplified vehicle operations, removing the second pilot, make a huge dent in the cost structure of some operators. Then you actually enable new use. Another example, you enable new use because you can fly denser at the same safety level. So currently, the system of rules in the air, there's two systems of rules. There's the instrument flight rules and there's the visual flight rules. In the instrument flight rules, everything works because the pilot talks over a voice link to someone on the ground who tells you, go up or down a bit or maintain this course so that nobody flies into each other. And that only works when everybody stays in their multiple cubic nautical mile bubble. So under these rules, under instrument flight rules, you could have one air taxi over London, and then everybody else has to stay out of London. So if you want to do air taxi operations, that's risk. Then you can go to the visual flight rules, where the responsibility to not fly into others is delegated to the pilot on board. And that works, you could have maybe 5 air taxis over London, but if it gets much denser, the probability of accidentally flying into each other becomes significantly higher. So you need help to fly these things less under control. The control of the pilot stays the same, but the time scale in which he or she has to make the decisions, can become a more comfortable one. And then by doing this, you create whole new markets. So this is always, in the venture industry, you should not just see how many people would want a faster horse. We take all the people that own a horse today and we see how many want a faster one, and that's our market for automobiles. That's maybe not the most productive way of thinking about it, because if the faster mode of transportation, or the safer mode of transportation, enables completely new markets that will hopefully justify the investment.
So this is interesting because I think many times when we talk about autonomous vehicles, it's usually on the ground. Of course, yes. Others like yourselves are working on autonomous aviation. But what's interesting about from an AI point of view is that while the peripherals like the lidars, radars, and so forth can be useful, the algorithms and the kinds of detection are going to be vastly different. So in other words, up in the air, you're not so constrained by a very small lane, or maybe a lane that's been kind of washed off and you don't quite know where the lanes are. But then now you're starting to deal with XYZ context at a very high speed.
Yes.
Also being able to actually project out in terms of if in fact there are 2 or 3 air taxis, how could their trajectory result in a collision, for example? So tell us about the development of the algorithms and the uniqueness of the aviation versus, let's say, the vehicles on the ground.
You hit the nail on the head. And actually, so I was looking into this automotive space where the startups were popping up, and where the competition was, growing while you were standing by and reading the news. But the interesting thing is that actually what inspired me is that the robotics problem of flying is actually much, much simpler than driving. So, driving is incredibly hard, and there's been this sort of, the bump of expectations and the trough of disappointment, this hype cycle in driving, because, it's 10 years since we were promised them and they're still not there. And that's because driving is actually very, very hard, because you have to understand the difference between a bicycle and a dog and a pedestrian and a stone and a traffic light and a traffic sign and a written sign that says no entry on Sundays. All these things are very, very hard, and you operate in a constrained environment where you can go left, right, and stop, or go faster, with other people who are behaving fairly unpredictably. In the air, everything is much simpler. Everything you can see, rule number 1, do not fly into, unless you're very, very sure it's the thing you want to land on. So that's why I thought with a relatively small team, you can actually solve this robotic problem. But then the hard part is that the safety stakes are so much higher, because with a car, you can get to zero energy in the system by gently applying the brakes. It's not always possible, it's not always trivial, but it's something you can always choose to do. With flying, you cannot hit the brakes. That's dangerous. The safe state for flying is called having landed, and it's also the hardest part of flying. So you cannot have a system that says, I don't know what I'm doing anymore. Let me switch over to this stupid system here that can land, because that was already the hardest job. So if you can do that, you could stay flying. And this puts you in a completely different corner of the design space, which also means that a lot of the automotive components, for example, are not directly applicable, because, it has to work. It cannot fail. And, it has to be triple redundant. And so for the algorithms, that means you have to, completely upside down the risk versus cost. It's in automotive, for example, and in consumer electronics, your processor is optimized for the average performance, for an average programmer to program. In aerospace, you care about the worst case performance, but our programmers can be a bit more expensive and dedicated, and can have a bit more of them. So for many of the parts of the system, that puts you in a different corner of the design space, which also makes it intellectually very satisfying to work on. But it puts these stakes upside down. And it brings me back to this, sleeping well when you're about to light the rocket. So these certification standards, they're actually a good thing. They're not this paper barrier that's, imposed there by a random authority that, wants to exert his or her authority. The regulator has been delegated the responsibility, by the public, to make sure that they're not put unduly at risk. And so you should not allow this autonomous AI to take over important functions in life unless you've actually, prove to yourself and to the regulator and to the public that these things are safe.
So let's talk about certification from the point of the fact that, at least with cars, to some extent, you can at least have some use cases that can, reasonably certify or test out, right? But in the case of a plane, to actually model that in real flight is almost nearly difficult. I mean, in the sense of you could have a solo flight, but you can't simulate, let's say, for example, 10 other planes or activities.
Yes, you can.
You could do it on a computer system simulation.
Yeah.
So my question is, from a certification from an FAA and the incomparable perspective, are they relying on the simulation model data? Or
That's definitely a large part, and we worked through that in great detail in this report with EASA, because the real data is scarce and it's precious, and you don't actually want to waste it on training your system. So training is this term that's used for fine-tuning all the parameters in the machine learned system so that it does, roughly on average what you want to do. And that's for that, the real data is far too precious. You want to save the real data for the final acceptance test. And there's a subtlety there. If you would use that data earlier on in your process, you are overfitting and you lose all guarantees that your system will generalize to deal with the actual uncertainties that occur in the wild. So it's actually based on the statistics and the theorems of learning theory that you have to carefully treat your data as independent. You have to independently sample your test and your training data to have any generalization guarantees that the error rate you measure in the lab apply in the wild. So for that, you actually need simulation to generate the orders of magnitude more data that you have. And then you have another interesting problem. You have to make sure that that's sufficiently realistic. And so there's many examples in machine learning where the machine learning algorithm, for example, to spot lung disease, learned to read the QR code from the Röntgen scan, from the X-ray scan, and cheated. It learned to cheat, and they're very susceptible to that. So you have to be very careful managing your data. So that, in turn, means that much of what's called design assurance, that's how carefully you look at you programming your lines of code in these aerospace standards. Much of that now becomes due diligence and insane scrutiny on how you treat your data and doing that properly. And so properly managing the simulation, properly showing that your simulation does not have these artifacts, and then having a final acceptance test that is on data that's completely held out from the complete development process, which is a subtle thing. That is the essence of the standard we proposed together with EASA on this matter.
Yeah, it's really interesting because from a regulator point of view, is that I think there's a certain method that they've been using, right? That does, of course, look at some of the simulation data to an extent. But I'm curious in the sense of, are the regulators really knowledgeable and ready to deal with essentially, the AI portion of it? Don't forget to visit astroperkins.com to register for our next quarterly events. Past and current speakers include Julianne Hough, actress, dancer, and winner of Dancing with the Stars; Damian Vaughn, former NFL player; Neil Gregory, Chief Thought Leadership Officer at the IFC World Bank, and many more. To register, visit astroperkins.com and click on Events.
Certainly willing to learn.
Okay.
And so we found a willing ear on both sides of the oceans, and we have no complaints about the level of interest and also the level of knowledge they bring. So this was actually interesting in this project we did with EASA, is in a sense they brought the table of contents and the vocabulary. And then, the table of contents is all the things they worry about. And the vocabulary is also, this is a different, safety engineering is a different discipline than academic machine learning. And for example, the word random is a word, it's an everyday word, but it means something very specific in mathematics and academia, and it means something completely different and also very specific in safety engineering. So to have these teams of experts from their side and our side work together to work systematically through all their concerns, that was a super fruitful exercise. And we will announce other things soonish. There's another thing that the regulator we found susceptible to. So software is already the odd one out among all the components in the aircraft. So any system except software in an aircraft, for example, a metal strut that holds two things together, you put it in a lab, in a refrigerator at minus 40 degrees and at plus 100 degrees, and you bang on it 50,000 times, and with statistic soundness, you establish that it breaks on average after 40,000 times. And in the manual for the maintenance for the aircraft, it says replace after 30,000 bangs. That's how everything else works. Now, with software, you can't do that. You cannot bang 50,000 times on the software because it will do 50,000 times the same things. And it's very hard to explore the complete input space if there are these discrete events and show that there's an expected error distribution in your software. So with software, the design assurance is to make sure that there are no bugs when it leaves the lab, at least no found bugs. And then you find one in the wild and you go, oh, everybody's really upset. You have to go back through a process called continued airworthiness to analyze how come you didn't find this in the first place. And then, you patch everything back together. With machine learned systems, you're actually back in the type of statistics with the strut. So you show 100,000 images to the neural network, and what it has to do is it has to draw a box around the airplane or around the runway. And it does this 96% of the time. So it's not 100%, it's 96% of the time. But you can engineer the rest of your system to deal with the missing 4%. But now what's important is that this 96% is actually true. And for that, you can use the same methods as the banging on the strut. So in a way, and this is actually ironic, by having systems that are, so this is the non-deterministic people talk about, they're not 100% correct, neither is the software. But by learning to deal with the software that can fail, but putting hard bounds on how often it fails, you may end up with safer systems than the ones where you try to prove that there is no fault, where everybody knows, that's actually not true.
Yeah, I think that makes perfect sense. Again, I think the thing that keeps on coming up in my mind is really, it's kind of been the case with most kind of regulatory bodies is, how do they keep pace with the pace of innovation? Because here you're trying to kind of create an entire new space, right?
Right.
Using these neural nets, and frankly, whether it's on the US side or on the Europe side, it's a new set of competency and capability.
Yes.
That the regulators have to build in order to properly certify and evaluate exactly what the claims are. So to me, it's a very much a partnership, collaborative approach.
Very much.
But it's going to be very interesting to see how things progress because of the fact that there's such a high dependency on your success as a startup, based on the pace that regulators also get up to speed as well. Go ahead.
No, I agree with everything you said.
Okay, so one question before our final question is, when you think about developing some of these algorithms, is kind of the nuances of an air taxi and the A to B type of a transit versus more like a helicopter pad type of a model where it goes from the rooftop to maybe a ground base, for example, and other use cases including cargo. How do those account for having to create new or customized sets of algorithms?
So that's actually a very interesting question, and it ties back to our idea that your algorithms should be able to pass the test for human pilots. So that's actually what we did. We took the FAA published commercial pilot license skill test, made a list of these are all the things that a human does, proving that he or she is adequate. And then once you have that, as a human pilot, you have the general skill of flying, and you get a type rating to be able to fly, this helicopter or this fixed wing aircraft. But the general art of flying is relatively uniform. So once you have the basic control of the aircraft sorted out, which in our case, we expect the aircraft manufacturers to give us an interface so that, we can fly that way or that way. And then we come in at the level of human timescales. So, 1 second and up, where you have to make the decisions. And so that's relatively generic. That said, if you want to now prove that it's safe enough, you wanna show to the regulator that they would like to see you crawl, walk, run. This is a favorite phrase from the regulator. Let's not try everything at once. And the way that works is you first start in restricted operations. So you fly cargo along selected routes. We show that everything works there. Then we add some more variation, meaning we add some more randomness, and we show that the system can deal with that. And that's how we think we can, with the same technology, build up the evidence that it's safe by going from specific routes to broader operations. But for the core algorithms, it doesn't actually matter. But for the proof that they are safe, this is the way to roll it out. And so this ties to the two halves of our company. So we have one half of the company, making the systems actually work. And the other half of the company, there's a lot of personal overlap, but the other half of the project, if you will, that go on are about, proving that it is actually safe. And so you have to do these things in parallel. And for that, it matters.
I wish we had more time. I think we ran out of time for today. So I've been joined by Dr. Luuk van Dijk, CEO of Daedalean. Thanks for joining today.
This was a pleasure.
Great. If you've enjoyed this episode, take a moment to rate our show on any podcast platform that you listen to. Scroll down to the bottom and push 5 stars. It's that easy. And as always, thanks for listening.